The key chemical property that all aromatic compounds share is their great stability. They're unusually stable. So the question is, what are the structural characteristics that they share that account for this stability? Well, in the case of benzene, for a long time, people were content to say, hey, this guy has two resonance structures. They're equivalent. Having two resonance structures means it's more stable. There's your answer. Well, in fact, that's no explanation. It's an observation that a particularly stable compound can have two resonance structures, and when they have two identical resonance structures, there's considerable stability, but it doesn't explain it. Arrow pushing lets us track what happens with the pair of electrons in a second pair and a third pair to go from one structure to the other. People became less comfortable about saying it's resonance structures that account for this stability when they saw the following chemistry. Cyclobutadiene, alternating single and double bonds, can be pictured as going from one resonance structure to another. They're totally equivalent, just like benzene. And it turns out not only is this not especially stable, but cyclobutadiene is especially unstable. And the 8-membered ring, cyclooctatetraene, again has two resonance structures. We picture a cyclic flow of electrons. The two resonance structures are entirely equivalent, so it should lend particular stability. But again, this compound is not especially stable. It's especially unstable when it's flat, which would be required for having these resonance structures. Then people learned that there are some ions that are especially stable. This 3-membered ring carbocation is especially stable. Notice it's going to have a p orbital on this compound that is empty. And there's a 5-membered ring ion. This is an anion that's especially stable. This guy has a p orbital. But because it's an anion, we know that it has 2 electrons in it. And let me show you one more. This carbocation is especially stable. Again, it has a p orbital that's empty. When we turn the drawings of these compounds and ions on their sides so we see the flat ring, it's clear that each atom in the ring has a p orbital. Take a look. When we put the hexagon of benzene on its side, we see 6 p orbitals all lined up parallel to each other in a way that lets them overlap. Above and below the plane, we can draw a circle that shows these guys completely overlapping. And the same thing is true for cyclobutadiene and cyclooctatetraene, the 3-membered ring cyclopropenium ion, the 5-membered ring cyclopentadienyl anion, and the 7-membered ring cycloheptatrienyl cation. Now remember, we said some of these guys are especially stable and some aren't. Careful inspection lets you draw the following conclusion. Benzene has 6 pi electrons. Cyclobutadiene has 4 pi electrons in its cyclic system. Cyclooctatetraene has 8 pi electrons. This cyclopropenium ion has 2 pi electrons. This anion has 6. And this cation has 6. And to help us keep track, I'm going to draw a circle around the ones that we said are especially stable. It's the species that have either 2 or 6 pi electrons. And I'm going to put a line through the ones that are unstable. Ones that have 4 or 8 pi electrons. Putting all this together, it was possible to formulate a set of 4 criteria that need to be met for compounds to be aromatic. Take a look. First, all aromatic compounds are cyclic. And each of the atoms in that ring must have a p orbital. Thirdly, the ring must be flat, which is another way of saying all the p orbitals must be held parallel so they can overlap. And fourthly, that cyclic pi system must have a defined number of electrons called a Huckel number. It follows the formula 4n plus 2. Because n is an integer that can be 0, the actual numbers for the formula are 2, 6, 10, and a big one would be 14, but 2, 6, and 10 are already all the numbers you probably ever need to know. So aromatic pi systems will either have 2 pi electrons, 6 pi electrons, or 10 pi electrons. And the ones we crossed out as being not aromatic had 4 pi electrons and 8 pi electrons. They didn't fit the Huckel number. Well, these criteria are all well and good, and it's important to know them. Compounds that meet these criteria will be aromatic. But why? You probably already have figured out that we need to use MO theory to look at the energy levels of the pi molecular orbitals for these systems. Take a look at this. The energetics for that cyclic 3-membered ring that we took a look at look like this. The light line defines the energy of a p orbital, and we see that there's one MO that's highly stabilized. That's the bonding MO, and there are 2 anti-bonding MOs that are destabilized. For a 4-ring system, the MOs look like this. There's one stabilized bonding MO, there are 2 non-bonding MOs, and then there's one destabilized anti-bonding MO. The energetics of a 5-membered ring look like this. 3 bonding MOs, 2 anti-bonding MOs. And for the 6-membered ring, which includes benzene, take a look. We have 3 bonding MOs, 3 anti-bonding MOs. The 7-membered ring, 3 bonding MOs, 4 anti-bonding MOs, and the 8-membered ring looks like this. Now that we've got the energetics staked out for the molecular orbitals associated with these cyclic pi systems, we can put the electrons for these cyclic pi systems in there and see what it tells us. For that cyclopropenium ion, it had 1 double bond and an empty p orbital, 2 electrons. There they are. They're both in a stable bonding orbital, highly stabilized relative to a p orbital. For the cyclobutadiene, there are 4 pi electrons, and when we fill those guys in, take a look. 2 of them are in non-bonding orbitals. They're not paired. They don't contribute to bonding, but because they have negative charge, they destabilize the molecule as those negative charges repel. This is especially unstable. When we look at the 5-membered ring that had 6 electrons, that anion has electrons that are all in stabilized bonding MOs. Again, especially stable because they're all energetically favorable compared to the p orbital. And benzene, same deal. 6 electrons, all in bonding orbitals, all especially stable. The 7-membered ring cation, 6 electrons, 3 bonding orbitals, especially stable. And the cyclooctatetraene, it's got 8 electrons. 6 of them are in bonding orbitals, but look at the other 2. Again, like the 4-membered ring, this 8-membered ring puts 2 of the electrons in non-bonding orbitals. They are not contributing to bonding, but they do repel because they're each negatively charged. This destabilizes the molecule. So now we see the pattern and then we see the reason for Huckel's rule. In every case that's especially stable, the number of electrons fits Huckel's rule. All of the bonding orbitals are filled, and all of the electrons are in bonding orbitals. And in the 2 cases that are anti-aromatic, destabilized, there are either 4 pi electrons or 8 pi electrons. Neither is a Huckel number. So ultimately, we understand the definition of aromaticity as simply having all of the pi bonding MOs filled, no electrons left over. Okay, so that all makes sense, but you ask, well, how do we know the energy levels of where I've drawn them? Very good question. And the answer to that is mathematics. And all of this has been done in a quantitative way. And what I've shown you about the relative positioning of these energies for the MOs is all accurate. There is good news. There's a shortcut for determining where these energy levels are that doesn't involve doing any mathematics at all. Take a look. This approach uses something called a Frost circle. And Professor Frost had the insight that you could take the regular polygon associated with each of these pi systems, place it with a vertex pointing straight down, inscribe it in a circle, and where the regular polygon touches the circle defines where there'll be a pi MO energy level. When applied to these systems, you get something that looks like this. The 3-membered ring, vertex pointed straight down, inscribed in a circle. There are 3 points of the triangle that touch a circle. Those define the molecular orbital energy levels. The same turns out to be true for the 4-membered ring, and the 5-membered ring, and the 6-membered ring, and the 7 and the 8. In each case, this very simple geometric manipulation gives us, in a relative sense, where all of the energy levels are for these cyclic pi MOs. Very clever. Makes me feel very smart because I can determine where those guys are without doing any math at all. So there you have it, aromaticity. Perhaps as you suspected, the root of a compound being aromatic is having a cyclic pi system with especially stable molecular orbitals all filled with bonding electrons.